This is lesson 10.1, finding composite and inverse functions. The learning objectives are to find and evaluate composite functions, determine whether a function is one-to-one, and find the inverse of a function. Let's begin with our first objective and introduce you to the composition of functions. The composition of functions, f and g, is written f of g and is defined by f of g of x equals f of g of x. So we read this notation, f of g of x, as, here it is in parentheses, f of g of x. Now, this is the way you will see it written in textbook when we compose two functions together. And this dot, this open circle, does not represent multiplication. Do not try to multiply the functions together when you see this dot. What we're really doing is we're taking the second function on the right and plugging it into this function on the left. Whenever I see this notation, I rewrite it as this notation. It helps my brain a lot, and I think it will help your brain. So we're plugging the g of x function into the f function. All right. This will take on more meaning as we practice. So let's hop down to example 10.1 and you will see me begin to compose some functions. Right? So whenever we're asked to compose functions, we're always given two functions. Like here's f of x. It's this linear function, 4x minus 5. And here's g of x. It's this linear function, 2x plus 3. And we are now asked to find f of g of x. Great. Like I said, I always rewrite f of g of x as f of g of x like this. It's very helpful. I recommend you do it. So here we go, f of g of x, like that. That's what we want to find. Well, that means I'm going to plug my g function into the f function. Let me show you a visual up above. So I'm going to take the g function's stuff, its definition, and I'm going to plug it in for x in the f function. That's what's happening. So I start writing the f function 4 times x, but I replace x with the g function stuff 2x plus 3. Great. And now I finish writing the f function with a minus 5. Okay, we have composed the two functions at this point, but we want to simplify, right? So just think of what you would typically do to simplify an expression. So we take 4 times 2x and we get 8x, and then 4 times 3 and we get 12, and we subtract 5, and we see, oh yeah, we can add our constants together. So I have 8x, and then 12 minus 5 gives me a plus 7. There we go. So once we compose the two functions, which I did right here, I composed them together, we then simplify, just like we would normally simplify an expression. Well, sometimes instead of composing f of g of x, like this, maybe we swap the functions, f and g, so it becomes g first and f second, right? So this is g of f of x. And a natural question will be, are these the same thing? Is f of g of x the same thing as g of f of x? Well, we're about to find out because we're about to compose these functions together, like this, g of f of x. Well, in this case, going back to the top two functions, I would be taking the f of x function stuff and plugging it in for x in the g function stuff, right? So it's kind of going the opposite way. So I write the g function, I start writing the g function 2 times x, and when I get to that x, I plug in 4x minus 5. And then I finish writing the g function stuff, right? The plus 3 here at the end. And there we go, we have composed these two functions. but it looks like we can simplify. So let's simplify. And we have 8x minus 10 plus 3. And I can combine the constants, and I get minus 8x minus 7 to finish. Great. So is taking f of g of x the same thing as taking g of f of x, right? Composing the two functions in opposite order. And I look at the results and I say, well, no, right? This one said 8x plus 7 was the result of composition, and this one says 8x minus 7 is the result of composition. So they are not the same thing, right? Opposite signs, not the same. So be careful. The order of composition matters. And now, just to make sure that you realize, hey, this is not a multiplication symbol that we're using here and here, let's practice actually using the multiplication symbol between f and g. So in a past chapter, we talked about multiplying two functions together, f times g of x. Yep, to rewrite that, we would say that's f of x times g of x. All right. And now we can multiply the f function stuff with the g function stuff, right? That's taking 4x minus 5 and multiplying it with 2x plus 3. Great, so I'll do that. 4x minus 5, multiplying that with 2x plus 3. And of course, your brain says these are two binomials. We should FOIL them to multiply them together. And so I get 4x times 2x, which is 8x squared, and 4x times 3, which is positive 12x, and negative 5 times 2x, which is negative 10x, and negative 5 times 3, which is negative 15. I see some like terms that I could combine together to simplify, like positive 12x minus 10x, that's positive 2x. And so now I have my final result of multiplication of these two functions. Okay, so that is multiplication of functions when we see the multiplication symbol between those two functions. That's to clarify that these are not multiplication of functions. These are when you compose two functions together, plugging one function into another. Awesome. Okay, we're going to move on to example 10.2, and once again, we're going to have some functions like f of x equals x squared minus 4, this quadratic function, and g of x equals 3x plus 2, this linear function. And we are going to be asked to find f of g of negative 3 and g of f of negative 1 and f of 2. Okay, that's our goal. I'll do them one at a time. One thing to observe is in our past example, we were not evaluating the functions when we composed them. We just had the variable x. Okay, so this is giving us general compositions. Now, in this case, we are actually not only composing the functions, but we are evaluating them with a value replacing x. Okay? Now, there's two ways to get this done. I'll do it uh, the different way from what we've seen so you can see kind of the concept between this. Let's go on. F of g of negative 3, I'm going to rewrite it as f of g of negative 3, like this. And I recommend ignoring this outside function and only looking at the stuff inside the parentheses, the big parentheses. And that's g of negative 3. Now, I can input negative 3 into the g function to get an output. And that's what I'll do. So I'm going to say, what's g of negative 3? Well, that's equal to 3 times negative 3 plus 2. Okay. Cleaning that up. Well, that's negative 9 plus 2, which is negative 7. I have just found out that g of negative 3 equals negative 7. And so I can replace g of negative 3 with negative 7. Rewriting this stuff, I have f of negative 7 now. Now what I do is I take -7 and I input it into the f function, right? F of -7, that's what I want to find. That is -7 squared minus 4. Okay, I'm going to say that's -7 squared minus 4, which equals 49 minus 4, which equals 45. This is the output of what I started with. F of g of -3, its result is 45. Let's try another. This is g of f of -1. The first thing I would do is rewrite it as g of f of -1, like this. And that helps me to know, hey, looking only at the inside stuff, f of -1, well, I can plug -1 into the f function and find a result. So let's do that. So I have the input of -1 into the f function, which results in -1 squared minus 4, right? I'm using the defined function, plugging -1 into it. Now I clean it up and I say, well, that's equal to, well, -1 squared is +1 minus 4, which equals -3. Cool. So f of -1 is -3. And so I'm going to go and replace f of -1 with -3. Great. And so now, to finish this problem, I'm going to take -3 and plug it into the g function. Okay, so it's like going up here and plugging -3 in right here and right here, and I find out that g of -3 is equal to 3 times -3 plus 2, which equals -9 plus 2, which equals -7. We've done it. So g of f of -1 equals -7. Great. Now, we don't always have to use two different functions to plug in. I could plug the same function into itself. So in this case, f of 2, I'm plugging the f function into the f function and evaluating it at a value of 2. Now, of course, it's great to rewrite this in this format that I'm writing now. So f of 2, well, my main goal right now is to find f of 2. Okay, so I'm going to plug 2 into the f function, right? Going back to the definition of that function, right? I would then say, oh, f of 2, that's equal to 2 squared minus 4. And 2 squared is 4, and 4 minus 4 equals 0, so that's my output. I now know that f of 2 equals 0, and so I'm going to go over here and replace f of 2 with 0. I now have f of 0. Well, that means I can just plug 0 in to my f function to get the final result. So I do that. I'm going to plug 0 into the f function. And I get, well, 0 squared minus 4. And that gives me an output of -4. Great. So f of 2, when I work everything out, is equal to -4. That's the final result. All right, so we have just worked on composing two functions together, whether generally, when we're dealing with the variable x, or when we have to evaluate the composition of functions at a certain value, like -3, -1, or 2. Let's move on. And now let's change our objectives. Our next objective is to determine whether a function is one-to-one. The definition of a one-to-one function, well, a function is one-to-one if each value in the range corresponds to one element in the domain. For each ordered pair in the function, Each y value is matched with only one x value. There are no repeated y values. Great. So example 10.3, for each set of ordered pairs, determine if it represents a function, and if so, if the function is one-to-one. Here is a set, and it has 7 ordered pairs in it. Okay? First, we need to determine if it's a function. Now, you'll recall from past lessons that a function has only one y value for every x value. And it passes the vertical line test, right? There's only one y value for every x value. Now, a quick way to determine whether something's a function is to look at all the x values and say, are there any repeated x values? And if so, do they have different y values? So I'm only going to analyze the x values to determine whether this thing's a function. So I look at the x values, -3, -2, -1, 0, 1, 2, and 3, and I don't see any repeated x values. All of them are different. Okay, so that's why I'm going to say this is a function. This represents a function. Great. Now, the next question is this function one-to-one? That's our new concept. Is it a one-to-one function? And so to check, we look at the y values. And we want to first see if there are any repeated y values. And if the answer is no, then the function's one-to-one. And if the answer is yes, then we check the x values associated with those repeated y values, and we ask, are they different x values or are they the same? If they're different x values, then the function is not one-to-one. Let's just show you. So I'm going to look at the y values, and I'm going to say, oh, here's a y value of 27. Is there another repeated y value of 27? Well, yes. And they have different x values. This 27 has an x value of -3, whereas this 27 has an x value of +3. So this function is not one-to-one. All right, so if you have repeated y values, which we do in this case, with different x values associated with them, then the function is not one-to-one, and we stop right there. In fact, this function wasn't just not one-to-one because of these y values, but look at these y values, 8 and 8, and they have different x values. And 1 and 1, same y value, and different x values. All right, so that's why we're saying this function is not one-to-one. Let's look at another example. So here I have a set of ordered pairs, x, y coordinates, 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. And I first check to see if this is a function in the first place. So I analyze the x values, and I first ask, are there any repeated x values? So 0, 1, 4, 9, 16. There are no repeated x values. So I can happily say that this set represents a function. Okay, now the next question, is this function that I now know this is a function, is this function one-to-one? And so I analyze the y values, and I say, are there any repeated y values? Looking at the y values, 0, 1, 2, 3, 4. There are no repeated y values. Okay? And so if there are no repeated y values, we know that the function is one-to-one automatically. This function is one-to-one. Why do we call it one-to-one? Because one-to-one means there's only one x value for every y value, and also one y value for every x value, right? So that's a great name to give it. It helps me remember there's only one x value for every y value, and there's only one y value for every x value. Now let's see this visually. It helps a lot to see visually, what makes a function one-to-one. And so there's something called the horizontal line test. In the past, you've learned about the vertical line test. If you scan a vertical line through a graph of a relation, and you only touch that relation one time ever maximum, then that represents a function. Now, the horizontal line test, if every horizontal line intersects the graph of a function in at most one point, it is a one-to-one function. Okay, so determine whether each graph is the graph of a function, and if so, whether it is one-to-one. And so we'll run a horizontal line test. Here's my horizontal line I'm getting out. And I'm going to scan that horizontal line up and down. So here it's scanning through the graph window, and it only touches this red line one time ever. It doesn't touch in more than one location as I scan this up and down, okay? No matter where I put the line. Therefore, this function is one-to-one. Okay, so here it shows I'm only touching the red graph in one location, no matter where I put the line. Okay, so I will say this is a function. It passes the vertical line test, right? If I ran the vertical line test. And this function is one-to-one. Great, so we got a good visual of what makes a function one-to-one. Let's try another one. So looking at this graph on the right, I'm going to create a horizontal line. And I'm going to scan that line so it goes up and scans through the entire graph. I'm going to just make it move up in space. And as it goes, it touches the red graph in more than one place. Okay, so you can see it's touching this graph in more than one location. And like if I put the line there, then there's the 2 points that it touches. Meaning there is more than one x value for every y value. There are 2 x values at this height, right, of 3. Anyway, this is a function because it passes the vertical line test. But since it doesn't pass the horizontal line test, this function is not one-to-one. All right. So there you go. We always look to see if a function is one-to-one so that we can determine whether a function has an inverse. And that's what we're about to talk about. So let's talk about finding the inverse of a function. This is our final objective today. Finding the inverse of a function. The inverse of a function defined by ordered pairs. If f of x is a one-to-one function whose ordered pairs are of the form x comma y, and its inverse function f inverse of x is the set of ordered pairs y comma x. All right, so if a function is one-to-one, it has an inverse, and its inverse swaps the x and y values. So the x values become y values and the y values become x values. All right, it's actually pretty simple. So let's look at example 10.5 to see this. Find the inverse of the function 0, 3, 1, 5, 2, 7, and 3, 9. Determine the domain and range of the inverse function. Great. First of all, asking, is this a function? They already said it's a function. It doesn't have any repeated x values. That's why it's a function. Looking at the y values, there are no repeated y values, right? So the function is one-to-one. If that's the case, we can find the inverse of the given function, right? So we represent an inverse function with this seemingly -1 power. It looks like a -1 power with the function f, but that's not a -1 power. It's not the same notation as an exponent. It's just saying that's the inverse of the function. That's the notation that is used. And so the inverse function swaps all the x and y values of each ordered pair. So the inverse function would have 3, 0 and 7, 2. Well, I'll put 5, 1 first. Right? I'll put them in the same order, 5, 1. Okay, then 7, 2, and then 9, 3. Great. All right, so a function and its inverse are just swapping the x and y values, right? We're just swapping x and y in each ordered pair, and then we're good to go. Now, to finish off this example, it says to determine the domain and the range of this inverse function. Now, a little reminder for you, the domain is just the set of all x values of a function. So the x values of this inverse function, right? I look at all the x values, 3, 5, 7, 9, that's it. And I put them in their own set. All right, we've written the domain. Now let's write the range. And that's the set of all y values of that inverse function. So the y values are 0, 1, 2, and 3. And we have now completed this example. Okay, moving forward. Example 10.6 says graph on the same coordinate system the inverse of the one-to-one function. Great. So looking at this, let's explain. This is a function because it passes the vertical line test. Right? If I scan a vertical line through space, no matter where I put that vertical line, it only touches this thing once. And it's one-to-one because it passes the horizontal line test. No matter where I scan this line up and down on the graph, it only touches it once. Since it is a function that's one-to-one, it has an inverse. And the inverse is just swapping the x and y values. So let's do that graphically. Now, it's important to look for very specific points like these points here, here, and here. Okay, and I'll even include these points here and here. So it looks like I have 1, 2, 3, 4, 5 critical points where these lines kind of change their slopes. And so what I'm going to do is I'm going to take each point and swap the x, y coordinate value and plot a new point in space for its inverse. So I see this point is -5, -3, this point here. And so I'm going to swap the x and y values, and I will plot it at -3, -5. All right, so -3, -5 is a point right there in space. Let me describe one more time what I've done. I've taken this point that's on this original graph, and it's at -5, -3. Swap the x and y value. -3, -5. That's the new location of this point for its inverse. Let's do it with this point. This point is located at -3, -1. Swap the x and y values, and you get -1, -3, and you plot that point. -1, -3. Next, let's focus on this point. This point is located at -1, 0. So its inverse point would be at 0, -1. And I plot that right there in green. Moving on to the next point, this is at 0, 2. And so I will plot a point at 2, 0, swapping the x and the y value. And I have one more point right here that I could swap the x and y value of. This is located at 3, 4. Right? 3, 4. That's the point. And so I'm going to swap x and y value and plot it at 4, 3 for the inverse point. And that's located right there. I'll do it in green. And I'm going to connect all of these points with straight lines that I've drawn in green. So I have this line connecting, and then this line, and then this line, and lastly this line. And I have now graphed the inverse of the original graphed function. Let me see here. Cool. We're ready to move forward. Now, we've looked at things graphically, and now let's think about things algebraically. The question comes up, how do you find the inverse of a one-to-one function with algebra? And you can follow this 5-step process to get it done. Step 1, substitute y for f of x. Step 2, interchange the variables x and y. Step 3, solve for y. Step 4, substitute f inverse of x for y. And then step 5, you could verify that the functions are inverses by looking at them. Okay, so this is the quick step process, and I'm going to use this, and I'll show you how it's done. In example 10.7, we want to verify that these two functions are inverses of each other, meaning that their x and y values are swapped. Okay, f of x equals 5x minus 1, and g of x equals x plus 1 over 5. So if I want to verify that this function is the inverse of this function, I can go through this 5-step process. Let me do it. Ready? First, change f of x into y, because that's what f of x is. It's y. Great. That's step 1. Step 2, interchange the variables x and y, meaning swap them. Turn y into x and turn x into y. Because isn't that what an inverse function is swapping the x and y coordinate values? That's what we saw in the previous 2 examples. Okay, now step 3, solve for y. So our goal is to use algebra to get y alone. Therefore, I would add 1 from right to left and divide by 5. Okay, so that's what I'm going to do. I'm going to show it to you little by little. I'm going to add 1 from right to left, and I get x plus 1 equals 5y. And now I'm going to divide by 5. The entire goal is to get y alone. Well, now that I've done that, I get y, it's equal to, well, x plus 1 over 5. Cool. And now I'm going to run the last step of substituting f inverse of x for y. See this y right here? We got it all alone. Now we're going to call it f inverse of x. That is the inverse function of what we started with. And it just so happens that this f inverse of x equals x plus 1 over 5. It's the same as this g of x function, x plus 1 over 5. So I have just verified that the functions are inverses. F of x and g of x are inverse functions because when I go through this algebraic process, okay, I find out that, yeah, that matches. These match each other. Cool. Sometimes we don't have two functions to, to compare. We just have one function and they say find its inverse. Sure, we're going to go through this step process again. Let me do it just a little bit faster. Ready? Step 1, turn f of x into y, because f of x is y. Y is a function of x. Now swap your x and your y's, because that's what we do graphically when we have an inverse. The inverse is literally the swapping of your x and your y values. The next objective, step 3, is to solve for y. So I'll subtract 7 from right to left. And then I'll divide by 4. And I have now gotten y alone. Y is equal to x minus 7 over 4. We've done the algebra. Great job. Now, the last step is to turn y into f inverse of x. Okay, so this y is now rewritten as f inverse of x because it's the inverse function of what we just started with. Okay, so there's the answer. All right, so we just practiced doing this for a linear function, right? For a linear function, we found its inverse. Now let's go ahead and find the inverse of this function, f of x equals the fifth root of 2x minus 3. And so, yeah, this isn't a linear function. This is a radical function with an index of 5. So we're going to go through the same process, though. Well, y equals the fifth root of 2x minus 3. Okay, so we've just turned f of x into y. Next, we want to swap our x and our y, so I'm going to write this as x equals the fifth root of 2 times y minus 3. All right, so we just did step 2, swap your x and your y values. Literally just like replace y with x and x with y. That's all we do. Step 3 is the algebra part. That's where we use algebraic manipulation to get y by itself. And looking at this, I have a fifth root. And what undoes a fifth root? A fifth power. So we're going to apply a fifth power to both sides of this equation to start solving for y. X to the fifth equals 2y minus 3. And now I'm going to add 3 from right to left. So I get x, one sec, x to the fifth plus 3 equals 2y. Now I'm going to divide by 2 on both sides. And I've gotten y alone. Y is all by itself. It equals x to the fifth plus 3 divided by 2. And the very last thing is to take y and turn it into f inverse of x. Right? So I'm going to erase y. Okay, and I'm going to write y as f inverse of x, and I'm done. This is the inverse function from what I started with, right? So here's the original function. Here is its inverse. And we have completed this lesson. Great job. I hope you all are doing well, and I will see you in the next one.